I'm really, first of all, I want to thank everybody who invited me here. I'm really humbled and honored to be part of the conference, which is really going on great. And I want to thank the organizers, which are doing a great job of this. And I want to also thank Scalacy, which is a company that allowed me to be part of this. And the third thing, I want to thank the many speakers that are speaking today, because essentially they really influenced and given me so much in the past that I have learned from. And essentially, you will see this in the content of this presentation. I owe especially to Jonas Bonner because all the introductory part I could skim very easily, because if you saw the keynote today, everything's there already. So I encourage you to look at that essentially. So I'm Ivano. I studied as a physicist, but I immediately turned as a software developer. So I've been 20 years now in the industry, mostly doing backend applications on the web apps, then converted to web APIs, now doing big data systems. And I'm currently, been for a few years, a software consultant at Scalacy. So we're working mostly focusing on Scala as a platform. And my focus has been on a reliable and distributed system in the past years, essentially. And the company is a worldwide, totally remote consultancy. As we say, we specialize in delivering a scalable system, giving support and do auditing and consulting, and even designing whole projects from scratch. So we do both back end and front end. We have top-notch expertise, as I said, in Scala platform, but not necessarily only that. So we work to make your product better and faster. And now let's go to the presentation. I will give you an outline of that. I'm going to talk about introducing reactive systems, then introduce the CAP theorem, which is a relatively well-known result from the last decades. And that will lead us to talking about what I will call convergent data structures, which will lead us to the core and the meat of the presentation. We're talking about this late result, which is called the calm theorem, and how it relates then to the reactive principles. And I will give you a brief showcase in the end. And all the contents here is actually the result of other people research. There's nothing original here from me, but I will try to simply kind of wrap it up in simple terms and give an overview of connecting the dots and see how this impacts the approach that we take to build all our reactive systems. And there will be plenty of references and materials to research. And don't worry, because I have a closing slide, a final slide where I'll collect all the references for you. So you just need to take your picture with a phone or probably a screenshot with your PC and have everything there. So let's start with the reactive systems. I think everybody knows by now that they're built on these 4 pillars, which is the goal to be responsive, and this needs for a system to be built built on resiliency and elasticity. And this eventually leads to the choice of building message-driven architectures. And also was already pointed out that essentially we're talking about distributed systems. And this changes the perspective on how we approach the architecture that we're building, the solutions, and the overall design of the code and the architecture itself. Because as was mentioned previously, we need to focus on the fact that the distributed system have to handle possible failures in communication, the latency, which is going to slow down the system. Communication can be out temporarily, machines can fail. So the point is that we want to accept uncertainty, as it has been proposed by Erlang so many times. I will embrace failure. And this leads us also to, I want to also focus on the really insightful research and things that Mark Burgess says on his approach to this kind of system, talking about the promise theory. And I want to focus especially on the idea of working on a system which is made of autonomous agents. And the point is that these agents communicate not with the idea of sending commands to another part of the system that will respond always constantly, giving consistent results and immediate results, but you need to think of them as exchanging promises to deliver some value. And this approach kind of changes the perspective. So you build every part of the system to be somewhat able to handle the fact that these promises could fail to be fulfilled, and they need to evaluate what to do next, how to handle failure, how much to interact with that actor again later. And I will move now to the CAP theorem, which is really related to these fallacies of the distributed systems. It's a 2000 result, a conjecture from Eric Brewer from Google. And essentially, it focuses on these three properties of distributed data stores mostly, but any distributed system can face that. Is the 3 points are consistency, availability, and partition tolerance across the whole system. And essentially, the simplest basic view of this is that you, in the face of partition, you can only guarantee one of the other two, only consistency or availability. And this led in the first decades of the 2000s against this kind of simple separation between traditional data storage, which focused on having ACID properties, against this new introduction of this base guarantees, which means basically available soft state and eventual consistency. So we focus more on availability by handling this with eventual consistency. And this led to a whole lot of NoSQL, new SQL solutions, which were kind of inspired by this thing. But this dichotomy is not exactly so simple. First of all, what does it mean to be partition tolerance is not clear at all. Essentially because any system which is not under partition can be consistent and available, essentially. So there's a lot of research going on there. And especially I want to highlight this from Peter Bailey's, which kind of recorded all the possible level of isolation guarantees. And here I just listed a few. If you look at these, are all possible consistency guarantee that can be already fulfilled by having highly available system anyway. So you can have consistency with a highly available transaction. You only need to specify better what do you mean with consistency. And also Eric Brewer himself came back with a full kind of follow-up paper called the 12 years later CAP. And he also mentioned how the idea of CAP was to kind of throw a stones and a challenge to see how we could overcome the limitations of these systems. And in this paper, he outlines how everything should be focused on how you do partition recovery, essentially. And this could be based on a solution of using operation which commute, so you can exchange the order in which operations are essentially applied in different parts of your clustered system. And also on leveraging this, what I will call convergent data types. The idea of these data types is that you can merge these data structures later on, and independently of how you merge them, the order in which you merge them, the eventual result will always converge to the same data structure, the same data, which means that you don't need to actually guarantee that all the parts of the system see a single history of how operations are applied, because you can reshuffle them and convert to the same results. These data structures are usually called technically CRDTs, which means conflict-free replicated data types. And they essentially allow you to do optimistic replication as an approach, which means that different parts of the system can update their local data storage independently of the others, and eventually only later on share and replicate this data, because they can be merged on by different nodes in different orders and converge to the same results. And this has been studied by Mark Shapiro in between 2011 and 2018. In lots of publications, you can have the details there on the link. And this is kind of opposed to the idea of a strongly consistent replication, which means that all the nodes needs to agree beforehand to what kind of data are we updating and what's the final state of the system. And this data structures allows us to build interesting data structures. Sorry for the error. So, and we can start from simple counters, but then build on top of it to build sets and registers. You can find the literature on that, and there are even ongoing efforts to build some kind of standards with this replicated object notation, which looks a lot like JSON, but it's focused on the CRDTs. And generally, the idea is that you want to add information to this data structures and never kind of throw it out, so you can rebuild the eventual state of the system. And also the way you apply this merge operation between them have specific properties. And if I'm correct, Akka distributed data, for example, uses this approach, and even Cloud State with his own event sourcing results solutions. This is a very recent result from Martin Clapham, which is a researcher now at Cambridge University. And in this presentation, he's is showing all the things, all the pitfalls that you can get into when you try to implement this kind of solutions which are not easy to implement, not necessarily. So let's take a quick pause to reconsider what we've seen so far. And I want to focus on special aspects so we can move on to the rest of the presentation based on that. And regarding CAP, we see the relevance of it because we already see many systems in production which are essentially distributed big data stores or pipelines of data, machine learning models serving pipelines, microservice architecture, and it goes on, and it will become more and more pervasive as IoT takes over, and we get edge computing getting more and more important, also in the face of what it's called Industry 4.0, because essentially these devices are exactly designed to work offline. So we're so used sometimes to take the cloud and the network for granted. But in this case, you really need to think ahead of time on building solution where the single devices can be disconnected for a lot of time, and you want to have a consistent result in the end. Also, as already mentioned before my other presentations, I want to focus on the fact that the business perspective has changed with time. While in the beginning, you always wanted to strive for a strong consistency, guarantees, and eventual consistency was seen as something kind of suspect. And nowadays, we see that the actual business time frame is what matters here, because you can think of different problems you need to solve, starting from a shopping cart in e-commerce, a ticketing system for reservation on a plane, or for example, a high frequency stock market trading. You see that the time scale is totally different. You have different expectations, you see, on the real-time guarantees of these systems and the consistency. So after all, as Jonas was mentioning, this idea of having an instant consistency, it's a failure. It's kind of a projection of how we see things and the reality, but we always see some snapshot from the past, and this becomes more and more relevant if you look at the like a relativity physics level of approach to see that you need this information to reach you. So essentially, you want to really consider what it means for you to have consistency guarantees and what's the essentially acceptable level of stability that you need in your system. And the last two things are that the CAP theorem essentially outlines an impossibility result in the sense that it's a negative result. It tells you what you can't do with a distributed system or what you fall short of assuring or guaranteeing. And also, the whole idea is based on this storage semantics. So you see the system as some kind of data storage where you apply queries or updates, and the whole focuses on this aspect. And we see how we can change that approach. So to move on to the core and the meat of the presentation, we want to look at coordination. And I'll start with a simple example. Think of traffic of different freeways. The traffic is somehow representative of your information highways. And you have different way to cross this flow of information. You can have inline on-plane intersection, possibly with traffic lights, which actually have explicit coordination. So you have to stop one part of the traffic to let the other move on, and the other way around. Instead, if you have roundabouts, you have some sort of implicit coordination, and the flow is a little bit smoother, but you still have to take care not to bump into each other cars, especially if you have a truck going on your way and whatever. And if you think instead of having completely independent flows of traffic and with overpasses and tunnels, you kind of optimize with performance and throughput. So the idea is that this to have strong consistency in a distributed system, you need to use these coordination protocols. The most famous all are two-phase commit, but then the latest are well-known are Paxos or Raft, which are very hard to implement and have a huge penalty in performance if you need to do that. So the main point outlined by Amazon, for example, in his research, that you want to keep this coordination of the critical path of your request handling, essentially. If you can, you want to relegate that to the most far away part of your system if possible. And another thing that the research in this field has highlighted is that even on a single machine with a multi-core architecture that we have nowadays, you can have also bottlenecks on a single machine, especially if you have shared memory, which need to guarantee cache coherence, and you have multi-threaded architectures that needs to coordinate between cores and threads before they can switch contexts and so on. And they can be very taxing on performance. So the main point here is about coordination. Can we identify clearly which are the problems that can be solved consistently using a no coordination? And the dual is, can we figure out which problems actually can't do that, so we're safe and we can relax and say, okay, I need a coordination solution here. And to do that, to try to explain that, I'll make an example. We see here on the left a system that wants to figure out if we have deadlocks in the system and it's distributed. So we have a node on the left, one on the right. We see different parts process of the system which are waiting on each other for some releasing a lock, doing giving a response, and you have the risk of having a loop here that will deadlock the system. The point here is that this node itself can figure out, even independently from the rest of the system, that there's a deadlock. Even if he later on coordinate information with the rest of the system, adding this part of the system doesn't change the overall outcome because the system continue to be deadlocked. Instead, if we look on the right, we see a totally different situation where we have different nodes. We want to do garbage collection. So we want to identify which areas of memory are not referenced by the root memory object in our application. We see a node here. If we look only at this node and it looks at itself without interacting with the other ones, you can think that all the three memory objects here can be reclaimed by the garbage collector. But instead, as he coordinates with the rest of the system, we see this dashed lines that actually connects the green one with the root. So what happens here is that as the system grew to integrate the additional information, the original assumption is falsified. And so we have really totally different result. And this property that we have on the left is called monotonicity. In simple terms, there's a more strict definition here, but in simple terms, the point is that the bigger solution, adding more information and more part of the system, contains the result of a smaller one. So that's why it's called monotonic, because they go in the same direction. Instead, on the system on the right, the garbage collector, you see that this is not true anymore. As you add more information, the overall solution can change, can be falsified. And also we can see that we're not more focusing on the system state, on the storage state of the system, but we're focusing on the outcomes, which doesn't change between adding more information. And so this is all outlined very clearly in this paper from Stein and Alvaro from last year, which is called Keeping Calm. And the definition is essentially this, and the discovery, the main important result is that you can define consistency in terms of logical monotonicity. That's the acronym for CALM. And the core result is that they demonstrated that with this point of view, you can define a program which has a consistent coordination-free implementation if and only if the problem can be specified in monotonic terms. And this is a huge result because it really cleanly cuts the difference between one sort of system and the other one. And we now talk about the overall program confluence, because essentially you can give inputs to the system in different ways, in different order. You can batch them. You can send them to your system any way you like, and the overall outcome can be demonstrated to be the same. And let's make another simple example. You can think this is the essentially DynamoDB paper from Amazon. They researched the idea of building a distributed shopping cart. You see that as you add and remove items from the cart, you can build a data structure which essentially uses tombstones or logical cancellations, logical deletions, sorry, to keep track of the overall result. So you can reconciliate the overall system even if you add and remove things in different order between different nodes. Instead, when you do the checkout, you need to somehow sequence the operations on a timeline because you need to be sure of what's in the shopping cart before you're doing the checkout. A similar way, if you think of a ticket reservation system where you have no fixed date, essentially it means that you can grow the dates of the event and people can reserve their seats in however order they like and you don't care. And instead, if you have a fixed number of seats, the order in which this reservation comes in is very relevant, so you can't make it different in different part of the system, otherwise you're gonna lose consistency. And so it all boils down to using different solutions to reduce the necessity for coordination. So how does this relate to the CAP theorem? Essentially, one thing is that CAM reframes the overall CAP question in positive terms. And the other thing is that they relate because this coordination-free system essentially can be guaranteed to be available under partition as long as we talk about some form of eventual consistency somewhat. So they kind of solve all the three CAP guarantees. And as we saw, we moved the focus from storage mutation to program outcomes. And I want to align there's a follow-up research on this, which is on developing this as a language, which is called Bloom. And this essentially is similar to how you change approach from an imperative or a procedural language to the imperative one. So you want to highlight which are the things that are monotonic and which are not, because reassignment of a value of a variable essentially is a non-monotonic operation, and you immediately see which are the immutable data and which not. So here the Bloom language want to outline the line where you can have guarantees of coordination-free solutions and where you cannot. So how does it relate now to the reactive approach? We see that both promote the following, that there's a big overlap. Both promote to accept that eventual consistency is a very good solution where it makes sense. And as long as you need coordination, you want to keep it off the critical path. You want to use compensating actions and immutable data structures. And also, they both highlighted the how to leverage convergent data structure which have these merge-like operations, which have these three properties of being associative, commutative, and idempotent, which means essentially you can reshuffle the operation when you merge these data structures and converge to the same final outcome. Also, they build on using logical clocks for causal consistency and event-driven design. And here I highlighted the principles and patterns of the reactive foundation, and we see the high overlap. The other properties are less related, but they are related anyway, and we see there's a huge overlap in the approach. And let's see, is there any question so far that we can?
Let me take a look.
Mm-hmm.
Not so far. Anybody got anything they'd like to put into the? If you do have a question, put it in the Discord channel and.
Yeah. Okay. So we'll tackle them later on. Thank you.
Okay.
So let's move to the last part, which is about further research from the same lab in Berkeley. The same lab that came up with the common results. They actually experimented with an implementation of a system which follows this approach. And it's essentially a key value store based on actors, and it's capable of scaling on both axes, both horizontally and vertically. It's called Anna, and it's a partitioned multi-master system with weight-free execution, coordination-free consistency, which is a mouthful to pronounce, and it's not very clear, so we're gonna break it down a little bit. So to do that, we first need to kind of see what's the state of the art on key value stores and perform on key value stores, because this is what Anna has been compared on with on the paper, on the research paper, and the results that we're going to see. And essentially, key value stores perform better depending on how they're designed, and the focus seems to be shifted between single machines against multiple machines, which means that they have different solution and they're targeting performance on a single node versus a distributed architecture. On a single machine, what the state of the art uses is usually taking advantage of existing multi-core architectures. So they use lock-free programming models on high-performance system libraries, possibly. And they also try to reduce coordination by doing key partitioning. That means that different threads, different processes will distribute the keys, so you don't have to coordinate between these processes. And what we see is that usually this system focuses a lot on having strong consistency. And the limits that this brings forth is that there's a synchronization penalty even between cores and memory access. And this is crazy because if you look at the paper, you have a reference later on. Essentially, this kind of system can be the CPU. When there's a lot of high contention of some keys, the overall coordination between threads and in the shared memory can take up to 90% of the CPUs. So only 10% is left to address requests response cycles, which is really an incredible outcome. And also, for if you have workloads queues, which means that some keys are more hot, more requested than others, you might have some processes and threads which are actually underutilized because they're waiting for requests, while other ones can be like overloaded. And generally, this kind of systems are not tailored to scale out well because they're focusing on single node. And instead, on multiple machines doing distributed system, the focus is always on doing key partitioning, which is usually called sharding. And we see that different implementation choose to deliver different degrees of eventual consistency, but they're all essentially focused on this idea of a state machine replication. So the idea is that you take a snapshot of your system state and you replicate that on the rest of the cluster, and either by using a single master replication with the leader that takes the updates, or multi-master in coordination later on. So the limits of these is that, of course, we can have workload queues, which this time, when you have a hotkey, you might have some nodes which are handling more load while other are kind of unused. And also these systems are not necessarily able to scale in. With this, I mean that they're not tailored to be highly performant on a single node. And this kind of ruins the promise of elasticity. And also this state machine replication is essentially requires coordination, which brings back the problem and the performance penalty of having consensus, coordination across machines and so on. And instead, the design choices that they made try to overcome these problems. It exposes a key value API, a traditional key value API, and it tries to avoid coordination both in the shared memory architecture. They do key partitioning, of course. It's based on actor model, but here they pin every single actor is only attached to a single thread, and every thread is only attached to a single core. This is done to avoid any possible coordination needed between threads, okay? And this will lead to great benefits, as we'll see in a few. And also, they try to keep the replication of the state out of the critical path of the execution, so the request handlers. And the replication is done based on these CRDTs. Essentially, the actor state is an internal state designed as a CRDTs, which can be replicated across the cluster with convergent properties. And also what they found out that using a switch change in the exact data structure that you're using, you can guarantee different level of consistency. And yes. This is a very very simplified outline of how it works. They could have gone with a single master replication solution, where here we see every single actor handle a single key, and they have their own internal state. Their process is pinned to a thread, which is handled by a single core, and they have a queue of inbound messages. And here we have all users queuing their messages, and essentially we have coordination-free solution here, but everything here is limited by the throughput of every single actor. So you have a lot of requests on key one, you'll see the throughput is essentially limited by how many of those the actor can handle. And if I'm correct, this is essentially what is done by Akkar sharding, for example, as a solution, which guarantees you strong consistency across the cluster. Going to multi-master replication with coordination, we can have many actors handling the same keys and the same key range, essentially. They all receive a bunch of messaging in and they want to process, but before storing the updates, they want to coordinate between themselves. And when they reach an agreement between them, they update the internal state in a consistent way. But this is essentially very similar to distributed consensus. So what they did, they leveraged the idea of using internal state made of CRDTs, because now we have multiple actors sharing the same keys. The message comes in, every actor actually updates the states independently. They actually locally merge the different updates in a single overall outcome, and then at a kind of out of bandwidth, they share the updated state with the other actors by sending them to their message queues, and every actor will eventually converge to the same internal state. And this is a simplified view. There are a few more details outlined in the paper. One is that they use client proxies, which can which actually there's a front layer that accepts requests from the outside, and they need to distribute the keys to the proper actors, to the proper machines. They can use cache of the response or buffer of requests to get different level of consistency guarantees. As we said, they use a single actor per pin to a process and a thread, and they dedicate, each actor as a dedicated memory area. So they don't need to coordinate for cache coherence problems and these kind of things. And to communicate the replication, they use ZeroMQ. They use the in-process protocol to talk between the actors on the same machine, and the TCP with protobuf byte strings across nodes, essentially. And they also had a protocol to redistribute the keys in case of actor joining and leaving the cluster, the system, essentially. And how does it scale? On a single machine, we see that it rips a benefit because it almost has a linear scaling by adding on a single machine CPUs and threads. And also we can see performance optimization by the fact that each actor locally merges his own state before sharing it, which means less payload and less communication between the actors. And this also means that if you have a low contention on keys, this advantage is essentially lost because you don't have this replication extra. So you want to monitor hotkeys so you can scale up or down the actor replication factor. And when compared to a local, simple, low-level solution or with key value stores like Redis, essentially what we see is Redis is single-threaded, so it doesn't scale at all with multiple CPU and threads. The basic implementation using low-level libraries with optimized solutions or optimized APIs essentially scales up to a certain level, but then the coordination between threads starts to have a penalty. On multiple machines, this is even more highlighted because essentially ANA scales linearly as you add threads to the machines and nodes to the cluster, and it's incredible to look at the graphs, at the metrics. And also comparing this to Cassandra, for example, leads up to a scale factor of more than 10 per, where Cassandra at a certain point needs to coordinate between the different nodes in the cluster. Also, they made some simulated experiment with elastic scaling, and the response is very good. Now, so overall, this system outperforms the other ones because it tried to avoid contention and coordination. And they're also adding the rest of the development of the system is focused on doing dynamic monitoring of the keys of the requests, so they can scale in and out the system autonomically and in autonomy based on the load. So they also use different storage system in cloud. So when they want hotkeys, they want more performant retrieval of data, and for cold keys, they have more slow and less costly, more cheaper solutions, and it's basically available. They're doing it on AWS or commercially available cloud. So to conclude this trip, there are a few shortcomings which are very, very basic of the Calm approach. It's not all, blue skies and rainbows. First thing is that this monotonic programs don't always fit the problem at hand. So you have no guarantees that you can find a coordination-free solution to this, because it depends on the problem. And also, essentially, the Calm result is not constructive results. It doesn't tell you how to build a system. It doesn't give you a solution to verify that your problem can be solved in this way. So these questions are open for you to resolve. And as Martin Kleppmann I'm quoting one of his tweets in this past month, and that really seems to fit. It's out of context, but fits very well because it says that we open more questions instead of giving answers. And the takeaways of all of this is that there's a great overlap between the theoretical results of the Calm theorem and what was naturally came out of the industry experience with the reactive initiative, the reactive manifestos, because to get responsiveness and reactiveness, we want to avoid coordination using all these choices that we said before, like trying to fulfill the cap guarantees by avoiding coordination, if possible, using convergent data structure or keeping it out of the main path of execution. We using languages like Bloom, you can verify formally that your system is actually coordination free. And one other takeaway is that you don't want to abstract too much, because in the end, you also want to take into account potential bottlenecks at the hardware level, at the low, like system level programming. So to wrap it up, essentially, we don't have a clear solution ahead, but we have a lot of inspiration by existing system, by the experience of people that have worked in the past decade to build these great systems. And here we have all the references. I want to thank once more Scalasi, my company. We're doing, as I said, consultancy on this kind of system, and distributed systems, scaling solutions. We want to make your solution scale better and fast. If you want to discuss that with me, if you have questions, you want to discuss about anything, you can reach out our booth, virtual booth, in the coffee break room. So we'll make the slides available later on when they're ready. Thank you so much for staying with me here. I'm taking questions now, maybe on the Zoom channel or even here.